an astronomical event is coming that will stun the world. Scientists confirm the tiny star system T Coronii Borealis is a ticking time bomb gaining material and energy for an immense explosion in 2024. This blaze star will suddenly erupt, briefly blazing brighter than every other night sky object for a few days. Only this incredible cosmic flashbulb will be easily visible around the globe. But this brilliant burst may be a terrifying omen of a threat far beyond our universe. Let's dive into understanding novae and recurrent novae. This blaze star may seem like a harmless cosmic fireworks show, but the truth is, T Coronii Borealis hides an unexplained mystery deep within its core. As it prepares to erupt, could this tiny star system be a warning sign of something far more ominous lurking in the vast unknown? In the vast expanse of our galaxy, amidst the swirling constellations and the glow of distant suns, lies a fascinating and somewhat mysterious phenomenon known as a nova. These celestial events, while not as cataclysmic as their more violent cousins the supernovae, offer an incredible show of cosmic fireworks that can illuminate the night sky with sudden brilliance. Novae, particularly recurrent novae like T Coronii Borealis, are not just stellar phenomena. They are cosmic puzzles that have intrigued astronomers for centuries. To truly grasp the nature of a nova, it's essential to understand what it is and how it differs from other stellar explosions, most notably supernovae. A nova occurs in a binary star system, where two stars orbit a common center of mass. One of the stars is a white dwarf, a dense remnant of a star that has exhausted its nuclear fuel. The white dwarf leads a parasitic existence, siphoning material from its companion star, usually a main sequence star or a giant. This material, mostly hydrogen, accumulates on the white dwarf's surface, where intense gravity and heat trigger nuclear fusion reactions. The result is a sudden explosive release of energy that causes the white dwarf to brighten dramatically. This brightening is what we observe as a nova. But with T Coronii Borealis about to blow up and shine bright, the big question is, could this strange event reveal secrets about the mysteries of the universe? Now, you might wonder, how would this nova outburst differ from a supernova? The distinction lies in the scale and consequences of the explosion. A supernova is the terminal explosion of a star, resulting in its complete destruction and the release of an enormous amount of energy, often outshining entire galaxies and producing most of the universe's iron and heavier elements. In contrast, a nova is a surface phenomenon that doesn't destroy the white dwarf, allowing it to potentially repeat the process if enough material accumulates again. Recurrent novae are systems where the nova event repeats itself due to the continual accretion of material onto the white dwarf. Unlike classical novae, which might burst once and never again, recurrent novae like T Coronii Borealis flare up at intervals dictated by the mass transfer rate in their binary systems. This predictability makes them invaluable to astronomers who study the mechanics of accretion and the evolution of binary star systems. Imagine a universe where celestial clocks tick with the regularity of white dwarfs accumulating matter, only to release it in brilliant bursts of light. This clockwork regularity is rare in the cosmos, making T Coronii Borealis and its kin subjects of intense study. How often does this stellar spectacle occur? For T Coronii Borealis, the intervals are about 80 years, a blink of an eye in cosmic terms but a lifetime in human terms. Each outburst offers astronomers a fresh opportunity to peer into the processes that govern stellar evolution and binary star dynamics. But why should we, as mere observers on Earth, care about these distant fireworks? Here's a compelling reason. Understanding novae helps us grasp the fundamental processes that govern the universe. The material ejected by novae enriches the interstellar medium with heavy elements, which in turn can form new stars and planets. Moreover, studying these systems allows scientists to test theories of how matter behaves under extreme conditions, providing insights that no laboratory on Earth can replicate. And there's an even more intriguing aspect to consider. Could the study of recurrent novae like T Coronii Borealis help us predict or understand similar systems that might pose a threat to Earth? While the distances make any direct impact extremely unlikely, the energetic phenomena associated with novae, like high-energy radiation and cosmic rays, could influence our planet's space environment in ways we are just beginning to understand. But what if these cosmic outbursts are more than just firework displays? What if they are warnings from the universe itself about dangers lurking far beyond our celestial neighborhood? The 80-year cycle and current observations. In a shocking revelation, the scientific community has uncovered terrifying evidence that the mysterious blaze star T Coronii Borealis is gearing up for another devastating explosion, one that could shake the cosmos to its core. This recurrent nova ignites in a catastrophic outburst roughly every 80 years, and the latest data suggests we're next in line for a cosmic front-row seat in early 2024. Why do astronomers believe that TCB is about to light up the night sky once again? Well, the signs are undeniable. Recent observations have shown an increase in activity around TCB, suggesting that the white dwarf and its companion star are aligning once more for another explosive event. The material being pulled from the red giant companion has been accumulating at an accelerated pace, as detected through spectral analysis that shows heightened hydrogen absorption lines. This is a clear indication that the white dwarf is gorging itself on the fuel necessary for its next cataclysmic explosion. How does this technology help predict when TCB might explode? By monitoring the light spectrum emitted by the system, astronomers can literally watch the nightmare scenario unfold in front of their eyes. Noting subtle changes in the intensity and position of emission lines, these changes are indicative of the conditions within the white dwarf's accretion disk, the ring of material spiraling into the white dwarf. As the material density increases, so does the likelihood of reaching the critical pressure and temperature needed to trigger the nova. These spectroscopic readings are complemented by photometric data, which measure the brightness of the star over time. A rapid increase in brightness serves as the ultimate omen that the high-energy hell is about to be unleashed upon the unsuspecting universe. T Coronii Borealis is no ordinary star. It's a celestial time bomb counting down to devastation. This recurrent nova has fixated astronomers with its predictable yet terrifying cycle of explosions every 80 years. This unique star system, consisting of a white dwarf and a red giant, has had documented explosions in 1866 and 1946. Now, as we approach the 80-year mark since the last event, overwhelming evidence signals that another outburst is imminent. But this upcoming cosmic detonation could be the most destructive yet. If predictions hold true, T Coronii Borealis will suddenly erupt from a faint 10th magnitude object, requiring binoculars to see, into a blinding second magnitude star blazing brighter than the most famous luminaries for a terrifying few days. This eruption will offer a haunting observational window into the violent death throes of an exploding star system. The brief yet brilliant nova may finally reveal key mysteries about the catastrophic forces driving the recurring death cycles of binary stars. The 80-year cycle of TCB is particularly intriguing due to the dynamics of its binary system. The red giant continuously loses material from its outer layers, which then accumulates on the surface of its companion white dwarf. This material builds up until the pressure and heat trigger a thermonuclear explosion, resulting in the nova we observe from Earth. The cycle is driven by the mass transfer rate between the two stars and the efficiency with which the white dwarf can accrete and compress the incoming matter. Moreover, this impending celestial grenade may pack an even bigger blast than expected. Recent findings reveal not just one, but potentially two magma chambers lurking beneath the surface, adding a whole new level of complexity to the situation. The primary chamber, known since the 1980s, pales in comparison to the monstrous secondary chamber discovered more recently. Imagine a hidden reservoir of molten material just waiting to fuel future eruptions. Finally, satellite observatories like the Hubble Space Telescope and Gaia are our lifelines in monitoring this impending catastrophe. They provide vital, unadulterated data free from atmospheric distortions, painting a clearer picture of TCB's behavior and its position in the cosmos. Gaia, on its mission to map the Milky Way in 3 dimensions, is giving us precise measurements of stellar positions, distances, and movements, painting a clearer picture of TCB's antics in the galaxy. Now, let's confront the sheer gravity of what we're facing. If predictions hold true and TCB erupts in 2024, we are not just witnessing a cosmic event. We're witnessing a real-time laboratory for understanding the cataclysmic mechanics behind it. Astronomers are bracing for what may be the most critical live observational event in decades, dissecting the explosive death throes of a binary star system. Historical observations of TCB. As we brace for the impending cataclysm of TCB's potential nova outburst, let's rewind to the shocking historical eruptions of 1966 and 1946, revealing the terrifyingly unpredictable nature of this binary star system. The first well-documented eruption of this star occurred on May 12, 1866. Irish astronomer John Birmingham, an enthusiastic amateur skywatcher, noted a sudden brightening in the constellation Corona Borealis overnight. TCB transformed from a star barely visible even through telescopes to one of the brightest objects in the night sky. This 1866 outburst set the stage for TCB's recognition as a recurrent nova, though it would take another 80 years to confirm this categorization. Fast forward to 1946, and the role of amateur astronomers becomes even more pronounced. On February 9th, Leslie Peltier, an American amateur astronomer renowned for his contributions to comet and variable star observations, witnessed and recorded the second great outburst of TCB. His meticulous observations provided invaluable data that helped astronomers confirm the recurrent nature of TCB's nova episodes. Peltier described the event as awe-inspiring, noting the star's rapid brightening over just a few nights. The involvement of amateur astronomers like Birmingham and Peltier in tracking these events underscores the crucial role that these individuals play in the field of astronomy. Amateurs often serve as the vigilant eyes of the sky, providing the first alerts to changes that might otherwise go unnoticed by the professional community due to the vastness of space and the multitude of stars under observation. But what exactly happens during these outbursts? At the heart of TCB's system is a white dwarf, a stellar remnant that marks the final evolutionary state of stars not massive enough to end their lives in supernovae. This dense object is typically about the size of Earth yet contains the mass comparable to that of our Sun, leading to a gravitational field so intense that it can strip material from its companion star. White dwarfs are essentially the exposed cores of former stars, having shed their outer layers and ceased nuclear fusion. However, in binary systems like TCB, their story takes a dramatic turn. Orbiting this white dwarf in TCB is a red giant, a star in a later stage of its life having exhausted the hydrogen in its core. This causes the star to expand dramatically, increasing its radius and decreasing its surface gravity. The outer layers of a red giant are thus only loosely held by gravity and can easily be influenced by external forces, such as the gravitational pull from a nearby companion like the white dwarf in TCB. So, how does material from the red giant end up on the white dwarf, and what leads to a nova explosion? The process begins with the red giant's expansion, which brings its outer layers close enough to the white dwarf to be affected by the dwarf's strong gravitational pull. This results in a stream of material being transferred from the red giant to the white dwarf. This material accumulates on the surface of the white dwarf, forming an external layer of hydrogen and other elements. As this layer grows thicker, the pressure and temperature at its base increase due to the intense gravity of the white dwarf. Eventually, the conditions become right for hydrogen fusion, the same process that powers the Sun and other main sequence stars. However, on the white dwarf surface, this fusion occurs all at once rather than steadily. This sudden fusion causes a thermonuclear explosion, which we observe as a nova. This explosion blows away the accumulated material briefly, causing the white dwarf to increase in brightness dramatically, and in the case of TCB, making it visible to the naked eye from Earth. As we look toward the expected 2024 outburst, the historical data from 1866 and 1946 become even more significant. These records not only provide benchmarks for current scientists to predict and prepare for the next event, but they also continue to inspire a new generation of amateur astronomers to keep their eyes on the stars, ready to witness and perhaps discover something previously unseen. Scientific significance of the 2024 outburst. Now, what exactly do astronomers hope to learn from this event? One of the primary objectives is to deepen our understanding of stellar evolution. By studying how TCB behaves during its outburst, scientists can refine models of how stars evolve over time. This includes examining the processes of mass transfer between the white dwarf and its companion star, as well as the dynamics of the accretion disk, the swirling ring of material surrounding the white dwarf. These insights not only enhance our understanding of TCB specifically, but also contribute to broader knowledge about the life cycle of stars in binary systems. Furthermore, the 2024 outburst presents a unique opportunity to observe the process of mass accretion onto the white dwarf in real time. As material from the red giant companion accumulates on the white dwarf's surface, it forms an accretion disk, a swirling disk of gas and dust around the white dwarf. By studying the dynamics of this disk during the outburst, astronomers can refine their models of how mass transfer occurs in binary systems and how it influences the behavior of the stars involved. The 2024 outburst of T Coronii Borealis holds significant scientific importance beyond binary star system mechanics, offering insights into stellar evolution and the role of novae in producing heavier elements. It presents a rare opportunity to study a white dwarf nearing the Chandrasekhar limit, potentially leading to a Type Ia supernova. Comparisons with recurrent novae like Rs Ophiuchi and supernovae illuminate similarities in accretion processes, enhancing models for predicting future outbursts. Observationally, TCB's outburst in 2024 will be visible globally, accessible even to naked eye observers under optimal conditions. Future studies aim to unravel the dynamics of recurrent novae and their broader implications for stellar evolution using advanced observational tools.